To begin with this experiment, you'll see that I'll be using a non-contact infrared thermometer. It's a digital temperature gun with a laser function. These are versatile thermometers using infrared technology for fast and accurate readings in various situations, including barbecuing, cooking, maintenance, home repair, and other tasks. There's a built-in laser, as you can see from the little red light, that allows you to aim at your target. This particular experiment that we're going to be doing will utilize this gun and allow us to accurately determine what the temperature of the water is. Sir Isaac Newton, born on December 25th, 1642, was an English mathematician, physicist, astronomer, and a theologian, and also an author. He's widely recognized as one of the most influential scientists of all time, and is famous for discovering the natural laws of mathematics, which included classical mechanics, as well as optics, and the discovery of calculus. He's also famous for discovering the laws of motion and universal gravitation. Needless to say, he's well known in the scientific community. One of the laws that I enjoyed doing when I was in high school was a physics experiment pertaining to Newton's law of cooling. You see, Sir Isaac Newton created a formula to calculate the temperature of an object as it loses heat. The heat moves from the object to its surroundings. The rate of the temperature change is proportional to the temperature difference between the object and its surroundings. In this experiment, I am going to demonstrate this cooling effect, and then, using his formula, as shown here, calculate what the cooling constant is going to look like against time, as well as see if we could pull some other statistical information using the program R. So let us begin. We are using R version 3.4.4, someone to lean on. And we will now be talking about Sir Isaac Newton and his cooling temperature experiment. So to begin with, we will load the libraries as follows. We need a reader, and we need MGCV. I will now load the cooling temperature experiment, and I will just call it like that. And as you can see, I loaded it, and we get to view it. So we see the true temperature when at 0 it was 82.7 degrees Celsius, but the room temperature was 20 degrees Celsius, so you subtract the 2 and you get 62. And as time goes on, we get down to 155 minutes, and the true temperature is 26.8, but the difference temperature is 6.3. I'm going to load X and Y. As such. I'll close this window, make it nice and big, and now we will proceed to plot it. Plotting X and Y, you'll see right here you get a nice curve going down at 0. The temperature, as I mentioned, 60 something degrees, and it goes down to 6.3 degrees at 155 minutes. Now the nice thing about an exponential curve is we have a formula that we can use, where we can take X, which is the elapsed time, and Y, which is a function of X, in differential time. We'll just do a log of it. And to do this, I'm going to do a model. I'm going to make a model, call it exponential.model, and it's going to be a linear model with log of y as a function of x. There we go. And we can now do a summary of it, and we will see the formula, which is log of y is in relationship to x, and we could see the coefficients. The intercept is 3.981441, and x is minus 0.01458. And that gives us the log of y. So for the purpose, what I mean by that, if I look at the log of y, it's assigned 3.981441 minus 0.01480 times x. The nice thing about that is if I would simply just subtract this and just say y, while y is the exp of this, e raised to the power of that. And as you could see, the adjusted r squared value is 0.9889, so it fits the data very well. And the p-value is 2.2 e to the minus 16, which would suggest that it is very significant. Now, if I want to draw a curve here and plot the line, how would I do that? Well, there's a nice little value here, that a nice little trick, if you will, and I'm going to use the predict model, or the predict function of r, where I'm going to take the time values and I'm going to sequence it from 0 to 155 at 1 minute intervals. And the time, I'm going to create a thing here called temp.exponential2, which is going to be the exponential of a predicted value of the model that was created up here against the list of x, which is the time value. So the time values is again 0 to 155, step 100, step 1 I mean. Once I've done that, I can now plot it. I'm going to do something different with the plot. I'm going to make it a little bit more interesting. Here I am going to use x and y. The pitch or the thickness of the dot is going to be 16. Then I'm going to color it blue, and I'm going to put up here the main Newton's law of cooling, and x lab down here, x is going to be the time in minutes, and y lab is going to be the temperature in degrees Celsius. Let's go for it. Boom, there you see it. Newton's law of cooling, temperature in C, time in minutes for x, and you see I colored it blue. Now what I could do next is I'm going to put a line in there, and that's simply going to be lines, the time values, temp.exponential2, and I'm going to color that line red, just like that. So here you have it. If I zoom out, there you have it. You have the predicted values against the observed values. Pretty close. Now what's interesting here is I'm going to do a core test. Now I could do a core test here because, again, just to show you some differences, the core test is x against the log of y, and you could see that the core test is giving you a value that says it's 0.99459. If I now look at creating my data frame, and I use x log of y, and the model is going to be a function of log of y to x against the data, we'll summary it and plot it. So in summary, you could see the value is the same for the intercept and for x. The values of, or again, the p-value is again 2.2 e to the minus 16, so it all fits nicely. It's a 0.9889, and now I'm going to plot the model. When I plot the model, you will see that it's basically residual versus fitted is basically 0. It's expanded here for the purposes of, but really minus 0.1 to 0.1, that's 0. Don't let anyone tell you differently. This here, minus 1 to plus 1, is pretty well the same. Standardized residual, theoretical quantities of the log of y as a in relationship to x. It's a good fit. Again, not much change here. And Cook's distance doesn't even show up here as the dot dot dot. This is a perfectly straight line, and there are some variations, and you could see that in the plot here, but basically it's a good fit against the standardized residuals against the leverage. An interesting function is the GAM function, and for this type of a plot, I'll give you an example. Again, if I do the summary of G, the values again are very similar. So what this is telling me that is that, you know, this function of 3.98, as you can see, these values are just exact same thing. Nothing changes. You know, it's just another way of saying it. R adjusted is 0.989. Well, yeah, to 3 decimal points works. And what that means is the deviance explained is 98.9%. So what we're saying here is that the data fits 98.9% of the model. And that's it when it comes to Newton's law of cooling and how we can model an exponential curve. I hope you enjoyed this presentation and learned a little bit about not only the statistical importance of observing scientific data, but a little bit about Newton's law of cooling. Thank you for watching. Have a great day.